Alright, today we're going to continue on with section 4.1, and we're going to talk about differentiation and continuity and how those two relate. So we want to understand the relationship between differentiability and continuity. Remember, we are going to have a 4.1 quiz in 2 days. Alright, so first we're going to look at the alternative form for the derivative. So we know that we can use our limit definition, which has to do with the difference quotient, but that doesn't always work, or sometimes we're not sure because we might have like a piecewise function, for example, which we'll see in a little bit. So then we can use the alternative form of the derivative. So f prime of c is the limit as x goes to c of f of x minus f of c over x minus c. When we use this form, we can interpret or evaluate the derivative from the left side and from the right side because of the limits from the left and the right. So differentiability. Things that make something not differentiable at a point would be a discontinuity. So a hole or a break or an asymptote, if any of those occur, then the function is not differentiable at that point. A sharp corner. So, for example, f of x equals the absolute value of x at x equals 0 is not differentiable. It's differentiable everywhere else, but at x equals 0 it is not. A vertical tangent line. So f of x equals the cube root of x when x is 0. So again, f of x equals the cube root of x is differentiable everywhere except for at x equals 0. Also think about our example from the notes from last night. The square root of x. So remember, I had you find the slope, or find the slope at 0, and we know that it's undefined, but it's also not differentiable there at 0. If f is differentiable at x, then f is also continuous at x. So differentiability means continuity. However, the converse is not necessarily true. So what does that mean? That means that continuity does not always mean differentiable. And we can see that by just looking at, the cube root of x is continuous everywhere, but it's not differentiable at 0. The absolute value of x is continuous everywhere, but it's not differentiable at 0. Alright, so let's look at an example. Find the derivative at x equals c, or determine that it does not exist. So f of x equals the absolute value of x minus 4, and we want to find the derivative at c equals 4. So, spoiler alert, it's not going to exist, but we're going to look at, if we did the actual evaluation, how could we tell that it does not exist? So to do this, I'm going to use the alternative forms of the derivative. So we're first going to do the limit as x goes to 4 from the left of f of x minus f of c, which in this case is f of 4, over x minus 4. So this is limit as x goes to 4 from the left of the absolute value of x minus 4 minus 0 over x minus 4. Well, what is this limit going to be? Remember, we evaluated limits like this in our limit unit. I know that the absolute value of x minus 4 and x minus 4 are always going to have the same value. The absolute value of x minus 4 is always going to be positive. X minus 4 can be positive or negative. If we're approaching 4 from the left-hand side, then the denominator will be negative. So this will be negative 1. Now let's do the limit as x goes to 4 from the right of f of x minus f of 4 over x minus 4. So this is the limit as x goes to 4 from the right of the absolute value of x minus 4 minus 0 over x minus 4. And now, because we're approaching 4 from the right, the denominator is going to be positive, the numerator is always positive, so this will be positive 1. So what's our conclusion? Well, again, we already knew it was not differentiable, but this proves it to us because this is saying that from the left-hand side the slope is negative 1, from the right-hand side the slope is 1. Therefore, we can't make a determination for what the slope of a tangent line would be at 4. So therefore, it's not differentiable at 4. So f is not differentiable at x equals 4, and the graph does not have a tangent line at 4, 0. Alright, so I want you to determine whether the function is differentiable at x equals 2, then determine if it is continuous at x equals 2. So pause the video, unpause when you're ready to check your work. Okay, so here we have to evaluate the one-sided limits using the alternative form of the derivative. So I do the limit as x goes to 2 from the left of f of x minus f of 2 over x minus 2, which is the limit as x goes to 2 from the left of 1/2 x plus 1 minus the quantity 1/2 of 2 plus 1 over x minus 2. Simplify this, and I get the limit as x goes to 2 from the left of 1/2 x minus 1 over x minus 2. I still can't do direct substitution because of the x minus 2 in the denominator, so I'm trying to get that to cancel. So if I factor out a 1/2 in the numerator, then I have the limit as x goes to 2 from the left of 1/2 times the quantity x minus 2 over x minus 2. Those go away, and I'm left with just 1/2. So that is the limit from the left. Now I need to do the limit from the right. So the limit as x goes to 2 from the right of f of x minus f of 2 over x minus 2 is the limit as x goes to 2 from the right of the square root of 2x minus 2 over x minus 2. How do we simplify this? Well, we multiply the numerator and denominator by the conjugate of the numerator, which is the square root of 2x plus 2. Simplify, and I get the limit as x goes to 2 from the right of 2x minus 4 over x minus 2 times the quantity square root of 2x plus 2. Again, I'm trying to get that x minus 2 to go away, so I can factor out a 2 in the numerator. The x minus 2's cancel. Now I can do direct substitution, and I get 1/2 again. So I'm really excited because the one-sided limits are equal. Therefore, that's what the three little dots mean. F is differentiable at x equals 2, and if it's differentiable at x equals 2, I know that f is continuous at x equals 2. Remember, differentiability means continuity. The converse is not necessarily true. Okay. More practice of other stuff with derivatives. So now I want to find an equation of the line tangent, that is tangent to the graph of f and parallel to the line y equals 3x plus 6. So here we're going to go back to using the limit definition of the derivative. Using the difference quotient limit definition of the derivative, not the alternative form of the derivative. So I want you to evaluate or find the equation of the line that's tangent to this graph and parallel to the line y equals 3x plus 6. Pause the video, unpause when you're ready to check for work. Alright, so what's tricky about this is we know this is going to be the slope of the tangent line. The slope of the tangent line is 3 because it's going to be parallel to y equals 3x plus 6. So I need to find the derivative of the function and set it equal to 3 to find a point, or to find the point. That's the trick to this problem, is I don't know what point or what x and y value that I'm looking for. for the tangent line. So I use my limit definition. The limit is delta x goes to 0 of x plus delta x quantity squared minus x squared over delta x. Multiply out the squared quantity, x squared and negative x squared reduce, and then if I factor out the delta x squared, and delta x in the denominator reduce, so I have the limit is delta x goes to 0 of 2x plus delta x, which is 2x. So this is the derivative of the function, which is the slope of the tangent line at a point. So I set that equal to 3, because I know I need the slope of the tangent line to equal 3, and I can use that to solve for x, because that is going to give me the x value of the point at which I would get 3. So I get x is 3/2, therefore I can evaluate the function at 3/2 to find the y value. So f of 3/2 is 9/4, so then I know the equation of my tangent line that's parallel to the line y equals 3x plus 6 is y minus 9/4 equals 3 times the quantity x minus 3/2. Alright, last two examples we're going to look at are understanding the relationship between a function and its derivative graphically. So here I'm giving you the graph of g prime. I want you to sketch a graph of g. There are many correct answers, but there are a few characteristics that must be true. So for instance, the first thing we want to look for is if the derivative is 0, that says that the slope of the tangent line is 0. Well, what is happening on a function when the slope of the tangent line is 0? It's either at a maximum or a minimum. If the derivative is negative, so if I look, right here, the actual values of the derivative are negative. If the derivative is negative, what does that tell me about the function? Well, that tells me that it is decreasing. If the derivative is positive, what does that tell me about the function? It tells me the function is increasing. Here it's negative again, and here it's positive again. So again, there are many correct answers, but I know at these zeros, the function has to have a maximum or a minimum. Here, when the derivative is negative, the function has to be decreasing, and here where it's positive, the function has to be increasing. So one possible example, or correct answer, would be something like, let's put a point here, a point here, and a point here. And so then I'm just going to draw like that. So that meets my requirements, that when the derivative was 0, the function was at a maximum or minimum. When the derivative was negative, the function was decreasing. When the derivative is positive, the function was increasing. There are other things that we'll learn about when we learn about the second derivative, but for now, this is all we can, or this is the best we can do, is just have the correct increasing and decreasing, and the correct x values of a maximum or minimum. I don't know necessarily if this point was here, or this point could have been way up here maybe. I don't know that for sure, but I know that there was a maximum at that point. So here, you're given the graph of f. I want you to draw a possible graph of the derivative. So now you're using the similar thought process to what we just did on the last one, but now you're drawing the derivative, not the function. Again, there are many correct answers. So I want you to pause the video and unpause when you have a graph. Okay, so this is one possibility. Basically, what you have to have are these 2 points. Those need to be zeros on the derivative because those are maximums and minimums on the function. And here I can see the derivative is negative when the function is decreasing, and the derivative is positive when the function is increasing. Whether, this point here was arbitrary, it could have been higher or lower on here, I don't know that for sure. But the zeros and the increasing and decreasing need to be correct. Okay, so we need to make sure we understand the alternative form of the derivative, and that differentiability means continuity, but the converse is not necessarily true.